In the last two videos, we talked about inner product and we had this definition as well as the generalized definition, which also works for infinite dimensional vector spaces. Now we shall do the same thing with norm. We can just imitate this definition, expand with respect to a basis, and then work with the tuples, and then we shall get this definition, or we can work with this, then we shall get this definition. Now, since we already know that this is more general, works for even infinite dimensional cases, so naturally we shall focus our attention to this and not consider this at all. So that will be our definition 1 for norm. The second approach is as before. We take the definition of norm that we have already given, then we list all the useful properties of norm. That's a long list. We create a minimal list and then consider the conditions here as the axioms. Now, the universally accepted minimal list goes like this. The first property is, for any vector, norm must be greater than or equal to 0, and it can be 0 if and only if the vector itself is the null vector. The second property is, for any scalar alpha and a vector v, if I consider alpha times v and take its norm, then that will be equal to absolute value of alpha times the norm of v. Absolute value makes sense because our field is R. The third property is the celebrated triangle inequality. For all uv vectors, u plus v has length less than or equal to the total length of u and v. So here is our definition 2. Call a function, which I denote by this symbol from v to r, a norm, if it satisfies all these three properties. So these are the axioms. It is the axiomatic definition. So now we have got two different definitions of norm. One defined in terms of inner product and the other defined in terms of axioms. So we again have the same question. Are these two definitions equivalent? Is one stronger than the other? Let's answer that question. Now it is obvious that if you have a norm which is induced by an inner product, that is defined using an inner product, then clearly it must satisfy this definition as well. So I must have this arrow. So if something is inner product according to definition 1, it must also be an inner product according to definition 2, because the axioms are obtained as a list of properties satisfied by this, by the very construction. However, this implication is not true. And not only that, this implication may fail even for a finite dimensional vector space. Let me show you an example for something as simple as R2. For a typical vector x in R2, x1, x2, I define norm as absolute value of x1 plus absolute value of x2. This norm has a special name. It is called L1 norm. Now it is quite easy to see that this norm satisfies all the conditions of the axioms. So you are encouraged to check that, not very difficult. But I claim it is not induced by any inner product. Proving that a priori is not obvious, you just cannot take all possible inner products and keep on checking. There is a little trick which uses a result called the parallelogram identity, which makes the statement: you take any two vectors x and y, then x plus y, norm square of that, plus x minus y, norm square of that, will be equal to this, and you can visualize this as a parallelogram. So this is x and this is y, then x plus y will be this diagonal of the parallelogram, and x minus y is this diagonal of the parallelogram. If you add the squared lengths, then you get basically squared length for this, and this, which is this. Now it is actually easier to remember this as our familiar identity, like a plus b whole square plus a minus b whole square. So if you just expand it, you will get this result. Now the interesting fact about the parallelogram identity is that this holds if and only if this norm is induced by an inner product. Now proving one direction is very easy. If it is induced by an inner product, just use that a plus b whole square times plus a minus b whole square formula and you will get it. The converse is not that easy, so I encourage you to give it a try. Of course, you should be able to prove it. That is, if some norm satisfies this condition, it must be induced by some inner product. Anyway, we are not going to need that difficult task. Now it is possible to come up with an example such that your L1 norm does not satisfy this equality. That is, you can come up with x vector and y vector in R2 such that this side will not be equal to that side. It is quite easy to come up with such x and y, so give it a try. So you can say that L1 norm is not induced by an inner product, because if it is induced by an inner product, then this should have been satisfied. And that's all for this video.